Yeah, so I think for today, I'll like the idea would be to just talk a little bit about more about curvature, which we haven't. Tell you how that's related to the other characteristic. That would be like a good moment to stop before the spring break week, because after we return, then I'll try to circle back more to like how this is all related to the Poincare conjecture in 3 dimensions. But it was sort of useful, I think, to study in detail the case of surfaces, just because it's a little bit more concrete. So I'll still we'll need to talk about cool stuff related to vector fields and things like that. But probably we'll begin that after the spring break. Let me this. Let me just start by reminding you of what happened at the end of last time. So if you go to GeoGebra, I really recommend that you go to this website from time to time. Just play with it. Can everyone see like the huge sphere?
Yeah.
This is cute. So right, what I was saying last time is that well, there are a couple of things that I was saying. So the first thing is that you can you can take a point, right, on the surface of the sphere, and like just as before, you can think of a circle as those points on the sphere on the surface whose distance from a fixed point is a given number. So for example, I could like at this point A, which we took to be like the North Pole last time, but that doesn't really matter. Just imagine like choosing a random point on the surface of the sphere, and you find like your favorite radius, let's say 0.5. Okay. And so you can define the circle still on the surface of the sphere as the points whose distance from this given point is a fixed number. In this case, the circle I'm looking is like radius 0.5. And so that means like, well, again, it's easier to say if this were like the North Pole, just because like we know like some of the terminology in that case. But that's saying like if you had like a car on the North Pole and you drove like 0.5 miles in each possible direction from the North Pole, right? And then you stop after driving 0.5 miles, then like the possible points where you stop will have a circle. Okay. And again, the effect is more dramatic. Like the bigger the circle you make, just because like if you look at it from like from the from like observer in space, it sort of looks like a funny situation, just because the center of the circle, right? Like the center of the circle is not quite as one would think, right? Like the center of the circle like looks like it should be like sort of like this here, right? If you think about it, like from an observer on the outside. But like the thing is like if you only live on the circle, right? Like you're sort of applying the definitions the right way. It, like again, like this is really deserves the name center because all the points along this circle are at a fixed distance from this point A. So what else could it be? So if you were a flatlander, sorry, a flat earther, right? If you're a flat earther and you think that the earth is flat, right? Literally, you know, you would again choose like a point on the as your center of the circle, and you would just draw, like you would go like, again, now drive 1 mile in every possible direction, and just like say, oh, this makes up the circle. But then you find the interesting fact, right, that if this was a circle of radius 1, right, that means that it was radius 1 as you move along, say, like the meridians, right, along this you have, when I say that the circle has radius 1, I mean if you drive from this point to this point, it takes you 1 mile, right? But you know, as you're driving over the surface of the earth, right? So it's not 1 mile. I don't know if that's what, maybe with the second point it will be more clear. What I'm saying, right, is that when I say that this is a circle of radius 1, it means like it takes you 1 mile to get from this point to this point while driving on the surface of the earth, right? It's not that the line segment, right? The line segment connecting these 2 points is not 1 mile, right? It's a little bit actually shorter, but it's just that what, like, the point here is that you cannot, like, the line segment that goes through these 2 points, right? It's really not on the surface of the sphere. So it's not like really like a trajectory we can take if you want to connect these 2 points along the sphere. So like the point, like the idea of last time is that if you remember it, then with this, like, you would naively like apply your cute formula for this, like, so you would say, well, this is like a circle radius 1, right? So that is just like the circumference should be 2 pi times r, so it should be 2 pi miles or whatever. Well, this is a very small planet. But then when you measured, like, imagine like if you like put like a piece of string along that circle and you measure the length of that, you actually end up finding that that does not give you 2 pi. It actually gives you something a bit smaller, right? So meaning that, and so that you can take, meaning like on the sphere, what I'm like, what I ended up saying last time is that on the sphere, you cannot just like apply naively like the formula that the circumference of a circle is just 2 pi r, with this definition of r, right, of r being like the length of this arc connecting the 2 points. Is that making sense? And that's like actually, I mean, again, like this, you should think of this is like, because if you remember at the beginning of the course, we had discussed, well, how would you tell, for example, that the sphere is not like, it's actually, how would you tell that we actually live like on a curved space, right? If you cannot take like a spaceship and see the planet from the outside, right? And here there's like a sort of like an experiment that you could do to sort of test the nature of your space, right? So the experiment is just like draw a circle of radius r, measure the circumference of that circle, and check whether or not that gives you like the circumference gives you 2 pi r, right? And if it doesn't agree with 2 pi r, that means that there's some curvature going on of the space. And like what we're going to try to explain today is a little bit more about what this curvature is supposed to be. Okay. And so, for example, if by the same logic, we had also mentioned that like you could draw 3 points on the surface of the sphere, right? And again, these segments are sort of the closest that you ever get to straight lines on the surface of the sphere. Okay, these like circular arcs connecting the 3 points. So like the idea is that on the surface of the sphere, this has like every right to be called a triangle. Okay, this is as close as you get like to the usual triangles from that you know from on the XY plane that you would draw on the XY plane. So, and these do have angles, and it's just that if you add up the angles, again, like you will find that in general, the angles add up in the case of the sphere to something more than 180 degrees. Okay, so this would be like an alternative way to find that your space is curved, because like you would draw angles in the, sorry, you would draw triangles in the usual sense of the word, just like 3 points and the line segments connecting those 3 points. And then you find that the angles add up to more than 180. The extreme case that we did last time was sort of like the case of the equator. I don't know if you remember it, like 1 point on the North Pole, 2 points on the equator. In that case, actually, you can see that they had to add up to 270 degrees. In general, they can add up to like, it doesn't have to be 270. It can be less than 270, but usually like will be more than 180. Okay. So for example, before explaining you the concept of curvature, like there's a, so the sphere is sort of cute because like this is what's called spherical geometry. This is a version of non-Euclidean geometries, which some of you may have heard in the past. Okay. Like for example, again, like an interesting feature of this like in this particular case of this non-Euclidean geometries is that you can have like let's see. Well, right. Uh, right. There's like there's an experimental question, right? Like, right. For example, if I like, if you drew like a if you drew like a triangle, like imagine drawing like a very small triangle on the surface of the Earth, right? Like with your bare hands, like probably your experimental devices would not allow you to measure any effects from the curvature of the surface, right? Uh, and so you would not be able to detect, like you may just say, oh, this does not add up, does not add up to 180, just because like, you know, there's always some experimental error, right? So I mean, for all practical purposes, like the effects of curvature can be small enough that that you would first think that it's just experimental error over like thinking that there's like some interesting geometry going on, right? This is in a sense why Newtonian mechanics, like, you know, why do engineers still study Newtonian mechanics, or why do physicists also start studying Newtonian mechanics if supposedly Newtonian mechanics has been superseded by general relativity or like quantum mechanics? It's just because in order to like see effects of general relativity, you still need like strong gravitational fields, right? Like black holes, or there's also some effects from the sun that you can understand using general relativity, which you cannot use in Newtonian mechanics. But it's not like on a daily life, if you were trying to understand projectile motion, right? Like just throwing a ball to a friend. If you try to use general relativity for that, like that's going like on a kamikaze mission, because it just like you would use way more complicated equations and the effects would not be noticeable, right? Um, and the same happens like if you try to do quantum mechanics. So it's just that like, right, like if the effects, like the curvature can be sufficiently small that you would not be able to measure it in a useful way for most situations, right? You need to find like very extreme phenomena in nature and cross your fingers and hope that there you can get a chance to measure things better. Is that making sense? So this is why astronomers like, or cosmologists use like cosmic, like, you know, cosmic rays or things like that, which like to measure certain properties of the origins of the universe, because those come with a lot of high energy, And so there you like see some effects from special relativity and things like that. But yeah, in general, it's not like the effects can be subtle, so you may not like be able to notice those. Um, so right, it's a tricky question, but at least in theory, like right, if measurements were perfect, right? If measurements were really, really, really perfect, then getting the sum of the angles to be 179.99999999999, that's not 180. And so then you know that there had to be some curvature going on, for example, that it was not entirely flat. Okay. Uh, so that's the idea. But like the cool thing, like what you should really think is that this is like really a statement telling you that you could detect something about your universe. Like if you thought of the surface of the earth as the universe in which you live, that means that you can sort of tell features of its shape just by doing experiments within the surface, right? Within the surface of the earth, meaning that you didn't have to go outside with a spaceship to see that the earth was a sphere. At least there's some data that you can extract just by measuring properties of circles or measuring properties of triangles, which have the advantage that you can draw on the surface, right? So that's good because like in our actual universe, you don't have the luxury of taking like a spaceship outside the universe. Almost by definition, that's impossible, right? So it's good to know that there's like at least in principle some. Uh-huh. Uh, yeah, right, because like the idea is that the mass of objects like affect the curvature of a space-time. So like you would like you expect like the the triangle like the right like the triangles may not will in general would not add up to like say 180 or things like that in the in the in the presence of a massive object. Like what like this actually happens like if you make Google gravitational lenses if you want. Like the idea is like light, like something like light, right? Like usually when you think of light, you think of it like as traveling along a straight line, right? uh, but really strictly speaking, like you should think of light as traveling what's along what's known as a geodesic. I don't know if I gave you I don't know if I gave you like the name for geodesic last time, but geodesic is sort of like the fancy name for saying like something that behaves as close as possible to a straight line in these curved spaces. So for example, like a meridian or a longitude is called like a geodesic on the sphere just because that's like the closest curve that you have to a straight line. So in general, when you have something like the sun or like a star or a planet, I mean, in principle, again, everything bend like every piece of mass curves space-time. So there's always some effect. It's that again, this is related to the previous question that you cannot not always measure the effects. But in principle, yeah, like when light is traveling, it gets like its trajectory gets influenced by the objects nearby its trajectory, like where it's moving, and so it may bend and do other things in the presence of a massive object. So that's also similar to like I mean that's like a similar behavior to this thing about the triangles not adding up to 180 in general. Is that making sense? Yeah. So good. So in the case of surfaces, what happens is that really you have like one possibility, like, and I'll say this more precisely in a moment. So one possibility is like something like the XY plane, right? Like what's called Euclideans plane, the Euclideans plane, which is the one that you study most of your time in high school or before that, where like triangles add up to one, like the angles add up to 180. The formula for the circumference of a circle is 2 pi r. Then you have this spherical geometry version, where things change, as we just said. There's also another version, another possibility. Like the Euclidean model, the Euclidean case is sometimes called flat space because it's not curved. Again, I still haven't told you what curvature is, but the sphere is like the positively curved space. And then there's like a case corresponding to negative curvature, which is called hyperbolic space. That one is actually, that one is not too easy to explain without some formulas, for some reason, like for specific reasons, but at least let me show you how certain things look like in that case. Like, so I won't tell you necessarily how things get computed here. That's a little bit more tricky to explain. Anyway, like I don't know if you remember, like last time when we were discussing like distance, that I told you, well, like the distance between 2 points on the XY plane, right? Usually you use Pythagoras theorem. And so it's like the square root of x1 minus x2 squared plus y1 minus y2 squared. But then, like I also told you that on the XY plane, you could define like a different distance, which we call the taxi distance. Do you remember this taxi distance? Which is more like, oh, imagine if you were like a cab, like you cannot move along diagonals on a city. So it doesn't really make a lot of sense to define the distance between 2 points using Pythagoras theorem. You could just define the distance between 2 points like just by measuring the horizontal length and then the vertical length, right? Like, which are like the two sides of the right triangle, and then like declaring the distance to be the sum of those two sides. I don't know, that seems familiar. And so like the whole point of that was just to like give you the sense that like even like on something as well known as the XY plane, like there are like different ways to define the notion of a distance. And so in this other non-Euclidean geometry, which is called hyperbolic geometry, there's like, for example, you could think of like that you're working on the, now this is like not like a sphere, this is like really like the, imagine just drawing the unit disk, for example, on the XY plane, right? So the interior of the unit circle. And then you have to define distance in such a way. You define distance using a different formula. Again, like that's what's difficult to give without getting into too many details. But it's like a very deformed version of this taxi distance. It's just like an alternative to like using, it actually may use logarithms depending on how you define it. But the point is that regardless of how it's defined, then if you have 2 points here, the lines, again, by line, I just mean like what would be the path of shortest length under this new notion of distance. The lines between 2 points do not really look like lines. And I mean, again, like they actually get curved in some interesting way. And so, for example, here, like, again, like this, you would call, like all these segments that I'm drawing would be called straight lines in this world, or geodesics. That's a really fancy term for that. And so again, like you would have 3 points and you connect like the points using straight lines, and then like you get like a hyperbolic triangle, okay? And again, if you were to measure the angles of this hyperbolic triangle, then the Let's see. Okay, that one adds to 49.8. No, it's actually not. They're not related in that way. Yeah. It's not. It's not that you take like a straight line in the on the sphere and the projection or whatever would be these lines on the plane. Yeah. It's a. They're sort of like not constructed in that way. Yeah. Uh, Basically, like these lines. Are part of a circle. They're part of a circular arc which is perpendicular to which means this unit circle at 90 degrees. But yeah, the actual formula, like the actual way in which the lines are defined here, is just a little bit trickier to explain. But yeah, they're not coming from the lines on the sphere. But that's a good like guess. But yeah, it's not. They're sort of like one is like the yin, one is the other the yang. One is like good and the other is bad because like they're like opposite ends of the spectrum. Like in the sense that the sphere is sort of like what's positive curvature called positive curvature space, and this model, this hyperbolic geometry is like negatively curved space. So they're like complete opposites of one another. So they're not easily like they're not related in a straightforward way. Yeah. Let's see. So good. And so here, and what's the angle? Yeah. 25.66. Let's see. And so let me just cheat and use my cell phone to add up the numbers. So if you do 49.8 plus 38.23 plus 25.66, you get 113.69, which is less than 180, right? So in this case, like the angles in general add up to just less than 180. So this is why I'm saying that it's sort of like the extreme situation that the sphere, in the sphere that angles add up to more than 180 in this hyperbolic model, which actually Poincare constructed again. In this model, the angles add up to less than 180. And then again, you could like talk about a hyperbolic circle, which in this one does look like circle. I mean, and like, so for example, here I'm like drawing concentric circles, right? Like just circles who have the same center. And like, this maybe the effect is more, it's like the idea is like things are defined in such a way that like this distance is defined in such a way that somehow as you walk towards the, as you walk towards a boundary, as you walk towards this edge, it takes you more and more time to get there. So it really, it's sort of it takes you like a finite amount of distance. You can never reach the edge. Like the distance is defined in such a way that you can never reach the edge of the circle. So that's sort of like an infinite, like it looks at a finite distance, but it looks at a finite distance because you're still seeing, give me a second. Like, like for us Euclidean creatures, it looks like at a this finite distance because we're looking at it from our Euclidean perspective. But if you can sort of deform your vision and look at it from the hyperbolic point of view, you would actually say that like this edge is at an infinite distance from like say any of these points. So it's not it cannot be reached at a finite. This is why the circles, they sort of look like circles, but like they're not quite, you know, some points seem to be, they do not seem to be all at the same distance from the point A. But again, this is because of our biased view of these circles, right? We're not viewing them using the formula for the distance in this other hyperbolic world. It's just that writing the formula for the distance here is a bit more tricky. Is that sort of making sense? I'm just saying, like, there are ways to define distances in other interesting, even on the interior of the circle in the unit disk, you can define distances in such a way that other interesting behavior occur. So let's go back to the iPad. So in fact, like the idea is that you have like the Euclidean world, which is like the xy plane, say with the usual formula from Pythagoras theorem. And here, if you have a triangle with angles alpha, beta, and gamma, then alpha plus beta plus gamma, right, gives you 180 degrees. And if you have a circle with radius r, then the circumference equals 2 pi r, right? And then you also have, like, for example, the spherical world, where again, like the triangles may now look like this. I mean, bad picture. Triangles may look like this, and then you have alpha, beta, gamma, right? So again, this is sort of like our circle now, but now alpha plus beta plus gamma in general is less than one, greater than 180 degrees. And you could also look at a circles with certain radius r, right? And here the circumference is less than 2 pi r. That was, and then you have like the hyperbolic world. And again, like you can just think of it as being drawn as I was showing you inside the unit disk. But like here, that triangles sort of look flat. So they look skinny. So alpha plus beta plus gamma less than 180. And then you could also have circles of radius r. And then the circumference here actually happens to be greater than 2 pi r, if I'm not mistaken. So you see there's sort of like, in a sense, these two are opposites of one another, and sort of like this world sits in between them, sort of interpolates between the two. And like this is all related to curvature, so let me give you a sense of what curvature is finally. This is related to curvature. So in the past, if you had taken multivariable calculus, you may have seen a little bit about curvature, but that topic has been even deleted from the current curriculum. So probably not, none of you have really know how curvature is defined. And I will not give you like the precise definition of curvature, because that would again require talking a little bit about more about vectors and other things that are no. Right, good. If someone has seen tangent, normal, and binormal vectors, this is related to that. Yeah, yes, correct. It is very closely related to those vectors. Yes. So if you have a multivariable calculus book, you can just open the section on curves, and you'll see like a definition of curvature somewhere hidden there. It's just that now that topic gets skipped in class, so I won't go into that. But let's at least let's see if there's like an intuitive sense of curvature that we can agree on. Has anyone played Mario Kart? No one has. Well, if you played Mario Kart, right? Imagine that any of like these are like tracks, and you're driving, like you're competing with some friends. These are all supposed to be circles, right? Circles of different radii. So imagine that these are like different tracks that you can play on, right? And like they're like actually a Nintendo Wii. Is that how it's called? Right? Yeah, that's how it's called, right? The Nintendo Wii. Wii. Yeah. There are like some controls for Mario Kart which actually look like the steering wheels. Like, have you seen which ones I'm talking about? That look like you can do like with like almost like if you were driving the wheel of a like the steering wheel of a car. So like in which of these tracks do you think you need to be like sort of changing, like, where is there like a bigger risk of like just hitting a wall if you don't like keep turning around? Like, let's just call option 1, 2, 3, and 4, right? So where do you have to be like sort of steering the wheel or steering the car more and more so that you don't like exit the track? I don't know if my question makes sense. Ooh, good. Yeah. Is that clear to everyone, like intuitively, that on one, it's sort of like if you keep your eye, like if you get distracted, it's more likely that like you lose the game on number 1, because there you always sort of have to be constantly uh, making the car keep turning, right? Is that making sense? Good. Which means that what one would like to say is that when a circle has bigger radius, it is curved less and less. So for circles, one would expect that the bigger the radius. So for circles, the bigger the radius, the less it is curved. Is that making sense? So actually, I mean, it's not one actually ends up proving the formula. It's not by definition, but there's a definition of curvature for which the circle ends up having curvature 1 over r. Okay, so the curvature of a circle of radius r and so you see like uh, when the radius gets bigger, you're dividing by a bigger number. And if you remember this, like when you divide by uh, 1 over 1,000 is smaller than 1 over 10, right? So 1 over 1 million is smaller than 1 over 1,000. So the bigger the radius, the smaller this fraction becomes, right? So at least, again, however curvature is defined, it sort of makes sense that like this formula is somehow plausible because it's telling you the bigger circles have smaller curvature. Is that making sense? And then and again, like the point is that on a circle, right, every single point is sort of the same. And so that's why the curvature, like what we're saying is like the curvature of a circle at any point on the circumference is 1 over r. So like what you should imagine is that like since every point on the circle is sort of identical to each other, because you can, you just rotate the circle and you go to any other point, like there's no really good way of distinguishing points on the circle, then like every single point is sort of curved the same way. And so what happens for general curves, right? So what's the curvature in the general case? Well, so what ends up happening is like, say, take your favorite curve, think of it as like some sort of roller coaster. So maybe you have a point here P, you have a point here Q, you have a point here R, right? And so you see like this along Q, right? This like the curve looks more like a straight segment, right? You would like to say that segments are not curved, right? So maybe you would like to say here that the curve, like the point is like the curve is less curved here than say compared to P and R, right? And like the idea um, of how the curvature is defined, again, like there's like a general definition. Uh, that's close. Good. It's actually right. Like if you have taken calculus, right? You may have heard about the the tangent lines, right? Which are sort of lines that touch the curve like at a point and gives you the direction of the curve at that point, right? There's a again, like maybe most of you I think had taken calculus before, so this may look familiar to the majority. There's like a similar notion of, instead of like, a tangent line is sort of like the line that best approximates the curve, right? there's a thing called the osculating circle. And that's sort of a circle that best approximates the curve. I think it's also sometimes called the kissing circle. So like what I'm trying to say is that like in the same way in which you can define tangent lines, you can sort of define circles which are sort of barely touching the curve at a, I mean, there's like a precise definition of what the oscillating circle is. I will actually show you like an animation very soon. Give me a second, I'll find it. Let me switch to this other thing so that I can show it to you. It's, it's just taking a little bit of time, but it will soon work. This one is working now. And circle of curvature. Oh, good. Here it is. Can everyone see this Wolfram player thing about called circle of curvature? Good. So that's like the idea, like you see, like, so there's this curve, right? This actually looks very similar to what I was doing here. Ooh, good. Let's start here. So you see, like, there's this point on the curve, right? And there's this sort of circle that there's like, again, like a precise definition for how this is found, but there's sort of like a circle which is closest to the curve at that point. And then say, what happens if you start moving? Do you see that the circle is increasing in radius? Now we're approaching the part of the curve, a region of the curve where the curve looks more flat, right? So since the curve looks more flat, the circle has to become bigger, right? Because we said that the curvature of a circle decreases as the circle gets bigger, right? And as you're getting closer to a segment, like a flat piece of the curve, then the approximation should be using a bigger circle. And here, this is like an extreme situation where, like, for an instant, the circle becomes like infinite, like of infinite radius. So it's like a circle of infinite radius. It's like a line, basically, because it has zero curvature. And then it becomes normal. And the smaller the circle gets, that means that the curve is becoming more curved there, right? Is that making sense? And this is cute. And then you can change it with the curve. So you can wiggle the curve a little bit and see how the circle of curvature changes. But the idea is, again, like, this is not the definition of curvature, but it ends up happening to give you the right answer. Well, let's see. I think that could be true. Yeah. Yeah. Let's see. Let's see. I think that's true. Let me check for it. Just give me a second. Uh, yeah. Your intuitions are correct. So yeah, that seemed correct. So if you go like, I mean, as you might expect, curvature has to do with concavity of the curve in some sense, right? I mean, I didn't say that, but I should have said, like, the idea is like curvature is related to the concavity of the curve, like somehow. So like in the case of a function, like if you think of the graph of a function, like y equals f of x, then the formula for the curvature involves the second, like, again, it's a little bit complicated, but at least the numerator involves the second derivative. Okay. And so when at an inflection point, which is when the second derivative vanishes, right, the curvature would become zero. And if the curvature became zero, that means that you needed like a circle of infinite radius. If that is that making sense? Is that okay? And in fact, like what this is saying is that like, right. So what I was going to say again, like there's like a more general formula that applies not just for curves on the XY plane. But the idea is like again, like if this had like if this osculating circle had some radius at the point P, if this has some radius R sub P, and at the point Q, it has some radius R sub Q, then the at a point P on the curve, uh, the curvature is of the curve uh, is uh, curvature at P equals 1 over the radius of the oscillating circle. So basically, it like the curvature at that point agrees with the curvature of the circle of the circle. So it's 1 over the radius of the oscillating circle. Here it means in absolute value because it's possible to define the curvature in such a way that it's either positive or negative. Again, that's this sort of related to this concavity business, like that there's positive concavity and negative concavity, I suppose. But like, so this is like the in absolute value, because one can define the curvature with sign. One can since so that it is positive or negative. And in fact, so again, like as a remark, so for the graph of a function, like the formula for the curvature would be is like the one that I just showed you. Is sort of, again, like for those who have seen this, like the second derivative over 1 plus y prime was that sorry, y prime squared to the 3/2. Maybe that like could help some of you to have some intuitive sense of what the curvature is. So in this case, like the curvature when it's positive, like the second derivative is positive, the curvature is positive, so it's concave up. When the second derivative is negative, the curvature is negative, so it's concave down. And then inflection points, as was mentioned, the curvature would be 0. So that meant that the oscillating circle had radius, infinite radius, which means it's sort of like a straight line. And then, second derivatives have to do with acceleration, right? One way to think of second derivatives intuitively, if you think of physics, like, again, sorry if I'm saying calculus stuff, for those of you who haven't seen this, is that it has to do with acceleration. And this is also one reason why you can think of acceleration as being related to curvature. Is that making sense? So is that okay? And now the real cool thing is that you can talk also about curvatures of surfaces. And here's the trick. Let me show you again with the animation what this is. Okay. Can everyone see the Wolfram Alpha animation? Okay, so the idea is that you have like a surface, okay? You have a surface like this thing, which is called like a paraboloid. Again, if you eventually take calculus, multivariable calculus, you'll see surfaces like this. And then what you can do, again, I don't want to get too much into details, but you sort of like can like slice the surface, but like you can take like a plane that goes through the surface. Like, do you see this plane, like this piece, like this purple sheet? So you take this plane that goes through the surface, and like, again, for those who have seen it, like the plane contains like a vector perpendicular to the surface, like what's called a normal vector, but you can ignore that fact if you want. And do you see when you like think of this as slicing the surface? So when you slice the surface, you get a curve, right? Do you see this curve, like this black curve? So that curve, as we just talked, curves have curvature. So you can look at the curvature of that curve. And as you rotate the plane, right? As you rotate the plane, you get different curves, right? Which would have different curvatures in principle, right? But essentially what happens is that of all these curves, there's always one with the biggest curvature and one with the smallest curvature, okay? So for example, ooh, this is another cute one. So you have like you have a point on the surface, you cut it with the plane, you get these curves, and as you rotate the actually this it there was showing you the oscillating circle if you think about it, but the idea is that as you rotate the plane, you get different curves, and again these different curves have different curvatures, and there will be two curves with the of all these different curvatures. Like you select the one that's biggest and the one that's smallest. So similar, like again, here you have another surface, take another point, look at the different curves that you get by cutting it with a plane. And in the planar case, you look at the different curvatures here. In this case, there it was always 0. But like the idea is that, like the point is that like the summary of what I was saying is that if you take a surface, you look at a point, you cut it with the plane, you get a curve on the surface. So what you do is like cut the surface with planes, in order to get curves. Different plane which will have which have different curvatures as you vary the plane. And then you look at the smallest and biggest curvatures. Okay, you consider the smallest and biggest curvature. Call them like C curvature small, curvature big. And then the curvature of the surface is by definition the product of these two curvatures. And then the curvature at P is by definition the product of these two curvatures. So multiply the curvatures. Has anyone taken linear algebra? No worries. If you ever take linear algebra, these curvatures can be thought of as eigenvalues of a matrix, if that sounds familiar to some of you, but that doesn't matter. But like the important thing is that Gauss showed that this curvature can be computed just by measurements that take place on the surface of the surface itself. That this curvature okay. In fact, let's call this curvature C sub Gauss. The curve, like this is called the intrinsic curvature of Gaussian curvature. And like the idea, for example, is that well, let me say two quick things. So like for example, what would be the curvature of a sphere? That's nice to know. Well, if you cut the sphere with these planes, essentially what you get are circles, right? Yeah. Yes, because one has the torus can be given a flat curvature. Yes. So like what I was saying is like if you think about doing this on the sphere, you have to imagine cutting the sphere with planes, these sort of planes. Like the planes that you get when they cut the sphere into curves, they give you circles of radius r. And so the curvature of those circles is 1 over r. And so you have to multiply those two curvatures. And in this case, they are all of the same size. All the curvatures are the same. And so you just multiply them twice. And so the curvature of a sphere of radius r is 1 over r squared. Is that making sense? And then, okay, so there are a couple more things that I want to tell you about curvature, which I'll tell you about after the spring break. Let me just finish today by just mentioning something cool. So like you should think about curvature like as, like again, curvature can vary from point to point on the surface. The curvature can be different at different points on the surface. But there's a great theorem called Gauss-Bonnet, and this is like the only place where I'll write like an integral. So like I won't insist too much on this, so I will just mention it quickly in these 3 last minutes, which says that if you have a function, like if you have taken calculus 1, you can integrate functions, right? You could do like an integral of a function from 0 to 1, okay? Or from 0 to 2, right? Like you can integrate a function defined over an interval. There's like you can think of the curvature sort of as a function defined over the sphere or over other surfaces, and so you can take its integral, but now it's an integral over a surface again, like which is a lot more difficult to understand. But what Gauss-Bonnet says is that if you integrate the curvature, so if you integrate the Gaussian curvature over the surface, so this is like the integral of this curvature, you get 2 pi the Euler characteristic of the surface. Which is an amazing result. Which remember was the Euler characteristic, if you already forgot about it, which is totally fine, was 2 minus 2 times the number of holes, right? It was 2 minus 2 times the number of holes, which we call the genus, right? So for example, for the case of the sphere, it is telling you that the integral of the Gaussian curvature of the sphere, what would be the other characteristic of the sphere was 2, so that would be 4 pi. But for the case of the donut, right, the integral of the Gaussian curvature, what was the other characteristic of a donut? The donut had one hole, right? So it was 2 minus 2g. Is 2 minus 2 is 0, so that would be 0. So in a sense, this is sort of also one way in which you can distinguish a sphere from a donut using curvature, because on that sphere, the curvature always integrates to 4 pi. On a donut, the curvature always integrates to 0. And we'll see that there are cool consequences of this fact, but we'll discuss this next time. Again, like I won't mention too much this again about the integral, but I'll tell you a couple more things about curvature, which are good to know before moving on. So yeah, this is a good place to, and I'll repeat a couple of things that I just said quickly after we meet again from the spring break. But yeah, enjoy your break. yeah, you can you read the send me an email and I'll send you. I think this is a good book, a good introductory book. Good. Have a good one. You too. You too. Have. Good. Bye. I'll see you in 2 weeks then.